So today we are going to be seeing about the polarization in a little bit more detail, okay, however more visually. So as usual, I am going to use an Octave program to illustrate what we were talking about in the previous class. Okay. So I will start with the commands that I use all the time. I will also save this program. Okay. And previously we had discussed that the electric field can have components in the transverse direction, can have an x component and a y component, all right. And the amplitudes, peak amplitudes are given by Ex naught and Ey naught in the class derivation. So we will just start with simple cases. Ex naught, okay, is equal to 1, Ey naught is equal to 1, all right. Let us say that the components are equal in both x and y direction, right. And if we have a look at the nodes, we saw that the electric field has an x component, right, that varies with respect to time, and it has a y component that also varies with respect to time. However, it is not necessary that the y component is in phase with the x component. So to indicate that there could be a phase difference between the two components, we added a small phase over here. Okay. So we are going to use only this equation to understand what is going on, all right, because the final equation that we got is actually too hard for people to visualize. Okay. So we will be using only this expression and trying to see what is exactly this phase difference and what is the resultant, etc. Okay. So what we are going to do is we are going to write a program to just calculate E given Ex naught, okay, and say given some constant value of omega for different instants of time, all right, and for phase, etc. So we are just going to use this equation and write the program for today, right. So I am going to be starting with defining the value of phi. I am going to start with 0. Later on we are going to tweak all these values to reflect what all situations can happen. Okay. And I am going to keep this simple. Omega is equal to 1. Okay. So 1 radian per second is what we are using as a value. Okay. So now that we have defined all the right hand side values, that is Ex naught, Ey naught, phi and omega, all we need to do is with respect to time we have to calculate the resultant electric field, that is it. Okay. So I am going to take some amounts of time, right, for t starting at 0, okay, say going in steps of 0.1 to 10. Okay. So time is going from 0 to 10, I am taking some finer steps, okay, instead of going from 0 to 1 to 10, just taking smaller steps. You could always take larger steps, there is no issue at all. Okay. So Ex, right, we have to refer to our notes. Ex, by Ex we mean this entire term over here, Ex naught cos omega t. Okay. This is what is meant by Ex. Okay. So we go back to our program, we define Ex as Ex naught cos omega t. This is the definition of Ex, and Ey is Ey naught cos of omega t plus some phase phi, okay. And we will see the effect of all these things in a moment. Okay. Okay. Now the first thing that I want to do is understanding what is this Ex and Ey, all right, and what the phase difference is actually doing, right. So I am going to create a variety of plots, okay. I am going to create some 3 or 4 plots. One of them will show how is Ex changing, one of them will show how is Ey changing, another one will show how the resultant is changing, all right, etc. Okay. So I am going to create a series of plots. So I want to have 4 plots on the screen, 2 columns and 2 rows. So I am starting with a subplot 2, 2, and the first plot that I want, okay, is a quiver plot simply showing Ex and Ey, right. So I will start with quiver. So this is an arrow, I want to show the direction in which Ex and Ey are changing also. Okay. So I want to just show a quiver plot. Okay. I am going to use some slightly complicated arguments over here, but they mean very simple things. Okay. Okay. So, I want this plots, okay, to start at 0 comma 0, okay, and I will write down, draw an arrow to Ex 0 and 0 Ey. Okay. I will explain this line. Okay. What we are saying is we want an arrow going from say 0 comma 0 to Ex comma 0, whatever is the value that you have calculated using this program will have some number, okay, and it has to plot an arrow going from 0 0 to that number in the x axis and 0 0 to 0 comma Ey, that is the y axis. It is just a slightly complicated quiver plot, but you will get used to it. You can have a look at the reference manual for Octave for the quiver plot, but in essence whatever value of Ex we calculate, from the origin to that calculated value I want to draw an arrow 0 0 to that value. Same way 0 0 to Ey, I want to draw a vertical arrow, so I switch the order 0 comma Ey, etc. That is all we are doing, alright. For now what I will do is I will start with this and build over it. I know that I want to observe this with time, so I am going to pause it, okay, and I am going to run this program. Okay. It's running, that is good news, alright, but I observe that the arrows are changing, but the axes are also changing. That means we need to fix the axis to make any reasonable derivation. So I will have some extra commands over here, okay. So I will just say that I want to fix the axis and minimum x value that I want to have in the axis is -2, maximum x value is +2, so this covers the horizontal axis, minimum y value is -2, maximum value is +2, this covers the y axis, okay. On top of that, there is a tendency for Octave to use the maximum portion of the screen. Since the screen is rectangular, it tries to make the plots look rectangular, okay. So that is I want it to look square, -2 to 2, -2 to 2 should look like a square. So I can force that by saying that, okay, make the plot look like a square. So this will solve most of the issues that we have seen in the first run, okay. I'll just maximize this, okay. The horizontal arrow corresponds to Ex and the vertical arrow corresponds to Ey, alright, and with respect to time Ex and Ey are changing, okay. This is the first thing that we have to notice. Okay. Now that we have Ex and Ey changing with respect to time, we can start looking at the resultant, okay. So I will plot 2 comma 2 comma 2, the second plot in 2 comma 2, right. I want to be able to plot so the calculated value of Ex, calculated value of Ey, I just want to place a point over there, okay. Whatever is the calculated value, I am just placing a point on the axis, okay. And what I want to do is this has to go with respect to time, alright. I want it to change with respect to time, and I also want to have all the previous values, etc. So I am just going to use hold all, so it will retain the axis and all the previous plotted points in this run, right. And once again the axis is going to be looking a little crazy, so I am just doing the same axis command that I did before and I am pasting it over here. Okay. Now I am going to go ahead and run this. Now I get a second plot on the right side, and if you notice, it is plotting some dots on the right side. Okay. So we have plotted Ex comma Ey, which has been calculated, and with respect to time, what that indicates is just Ex along x axis, Ey along y axis, and the resultant is what you are plotting. You are just plotting the value of the resultant, and the resultant is just going along a direction which is diagonal, right. So, in this case Ex and Ey are equal, we have made it 1 and 1, and the phase difference that we have given is 0. So, let us look at this plot as to what is this phase that we are talking about. So, I will maximize. So, if you look at the left hand side plot, you will notice that Ex and Ey reach the maximum and the 0 crossing at the same time. So, the arrows increase, they come to the 0 at the same time and then they continue. That means that there is no phase difference between them. Okay? That is what is meant by the phase difference. Now, we could also do a few other things. It is not necessary that Ex and Ey have to be identical. They can also be not identical. So, I can just make Ey as 0.5, right, and Ex can remain at 1, and we can always see what happens, all right. We can see that the peak value of the horizontal arrow is higher than the peak value of the vertical arrow, but they are still in phase, that is they do the 0 crossings at the same time, reach the maximum at the same time. That is how you can understand what is happening with respect to the phase of these two components. If you look at the right hand side that you have calculated, the resultant now has a different angle with respect to the x axis, all right. It is more sloped to the horizontal side because the Ex is more, all right, but it does sweep a line. Okay, the locus of all the points for the resultant is still a line, all right, and in this case the line goes from the first quadrant to the third quadrant. Okay. So, let me make it back to 1 and let me continue with a few more plots just to make it visually more interesting, all right. And what I want to do is I want to create a new plot, subplot 2, 2, 3. Okay. In this case, what I want to do is I want to draw a quiver plot, but going from 0, 0 to the calculated value of Ex, Ey. So, from 0, 0, whatever is the calculated, previously we had plotted some dots, okay. That instead of that dot, it will plot an arrow going from the origin to that calculated dot, okay, because that is the way we draw vector fields usually, right. So, to just make that concept of the resultant clear, we just use this, all right, and once again I want to have previous values all intact. So, I am just using a hold all, and I want to keep the axis exactly same as all the previous cases. So, I am just plotting just copying and pasting the axis command going from -2 to +2 for x and y axis. Okay, I am going to go ahead and run the program. I will have a third plot. Now, the third plot is coming in the left hand side bottom, that shows the resultant, the calculated resultant, is going along this straight line. So, the electric field, net electric field with respect to time is oscillating about this line. Okay. So, spatially it is about this line, with respect to time it is going periodically between these two endpoints. Okay. That is what it means. Now, this particular case is known as linear polarization. Okay. Now, the condition for having linear polarization has to be examined in more detail. Okay. But before that, just for the sake of completeness, I will also have one more plot, just so that we have a different visualization, so that it becomes very strong in the mind, right. So, I will just plot one more plot, because I have some free space on the screen. I can just plot another, I can just make another plot. Okay. So, I will make a subplot 2, 2, 4 and I will make another quiver plot. Okay. Previously, I did quiver Ex, Ey, and I did hold all, that held all the previous values. So, the arrows were all visible. Now, I am just going to keep it simple. The current calculated Ex, Ey, whatever is the resultant, I want to have that alone, right. It is not a very informative plot compared to the previous one, but there is real estate. Sometimes this left hand side could get confusing, and I want to have some clarity on what is happening at the current instant of time. So, that is about it, right. So, once again this I do not want to have a hold all, I want to just have an axis command to fix things. Okay. Now, I run this, I have a lot of information available. Now, I can see the resultant only at the current instant of time on the rightmost on the right bottom plot. Okay. So, it is going between the lines. Right. Okay. So, now we are going to play with this program a little bit and try to understand all the other criteria. Remember that we have not made use of that derivation, that big equation that you got yet, all right. It means something. What it means can be explained only if you play with this simple equation and just try to plot what is happening. Okay. So, first, since we are here, let us observe all the criteria possible for linear polarization. Linear polarization, now it should be, starting point should be clear that Ex and Ey have to be in phase. They need not have the same peak values. Ex naught need not be equal to Ey naught. This is all we know. Okay. So, just to validate those things, okay, we can always create Ex naught to be 2, Ey naught to be equal to 1, all right, and you will still have you will still have a locus, that is a line created in space. Okay. With respect to time, the electric field at any instant will be moving about this point, right. That is what it means. So, the values of the electric field is going to change, the direction is also going to change within the time period. Right. So, condition for linear polarization is that the phase between the x and the y component is 0. Okay. But is it necessarily the only criterion, right? Now, let us go back, let us have a look at our equation, all right, 0, okay, phase is 0, okay. Now, 0 equivalently you can say that it is a periodic signal, you can also have 2 pi to be your phase difference, all right. But what if I make it pi? It is also, what if I make it pi, okay. If the Ex and Ey components are out of phase by pi radians, okay, then what happens? Okay. Now, one thing that we notice is the angle has rotated by pi. Okay. It is still linearly polarized. Okay. So, the criterion to be more precise for linear polarization is not that the phase is only 0, it could be multiples of pi. Okay. If it is 2 pi, once again you will get back your original result, but if it is pi, it is fine, it will go between the second and the fourth quadrant, but it is still a line that is swept by the resultant. So, criterion for linear polarization is, does not matter what your Ex naught and Ey naught are going to be, all that it matters is whether your phase difference between the x and the y components are going to be multiples of pi. Okay. That is the most generic criterion. This should be very clear. If you did not have a y component at all, right, okay, you will just be having the net electric field, okay, equal to the x component. So, it will look like it is doing this in space, right. So, this means that it is taking some positive values at different instants of time, negative values at different instants of time, that is it. So, in this case one can say that there is no Ey naught, right? There is only Ex naught, or easily you can say that the electric field has only an x component. Right? Okay. Now that this is clear, let us start looking at it in slightly different ways. We saw the case with 0 and pi, we know that 2 pi will give exactly the same as 0, all right. So, all of these are clear for linear polarization. Now we will go back to the simple case where both of them are equal. Okay. Instead of a phase difference between them to be pi, okay, previously it was 0, I will just make it say pi by 4, okay, or let us make it even weirder, pi by 5, alright, it is some value. Okay. So, Ex naught and Ey naught are equal and the phase between them is pi by 5. Okay. Now, another thing that also you can remember for this linear polarization before I do this is you can also have minus quantities. You can say that there is a lead or there is a lag. Okay. You could have minus pi to be the phase difference, right. Still you will sweep, okay, you will sweep a linear polarization. Okay. So, I will just hit a control C. It is perfectly possible to have positive or negative angles over here in radians. So, I will just go back to the case pi by 5 and I will just run this program, maximize this. Okay, we are plotting the resultant electric field in the bottom left. Okay. And at all instants of time. On the top, you can top right hand side, you can see that the points that are plotted is actually an ellipse. And you can notice from the first top left plot that the 0 crossings of the x and the y component do not happen at the same time. Okay, so, there is a phase difference between them. So, in the most general case, Ex and Ey can have different magnitudes. There can also be a phase difference between them. If there is a phase difference between them, you will end up sweeping an ellipse, alright. The ellipse will have a major and a minor axis. Now, we can always argue that this is the most generic case. Okay. Why? Because the ellipse has a major and a minor axis. Okay. If you make the minor axis equal to 0, it becomes linear polarization. Okay. So, you can always say that linear polarization is some subset of this elliptical polarization. Okay. So, the most generic case that we argue about is elliptical polarization, right. It has both the x and the y components to have different values and it also has some arbitrary phase between them. So, the chance that you will sweep an ellipse is very high. Okay. And then depending upon the major and the minor axis values, you can get either ellipse, you could also get a line, and soon we will be seeing that we could also get a circle. Okay. But before that, I want you to have a look at one more thing when we are doing this. Okay. If you look at the top right diagram, all right, the bottom right diagram and the bottom left diagram, it is very, wow, what happened there? Okay. One of the things that we notice is that the resultant is sweeping in the clockwise direction. Okay. It is going in the clockwise direction. This is also something that we need to note. Granted that it is sweeping an ellipse over a period of time, but it is sweeping the ellipse in some kind of a way, it is going in some clockwise direction. All right. This is something that we have to look for. Okay. Now, I will make this minus pi by 5. We can immediately notice that it is going in the anticlockwise or the counterclockwise direction, sweeping an ellipse, the same ellipse with the same major and minor axis is being swept in the opposite direction. Okay. So, that means even in this most generic case of elliptical polarization, you can have differences in the ways your electric field is going to sweep the ellipse. It could be in the clockwise direction or it could be in the anticlockwise direction. Okay. So, now people distinguish between these two also. Okay. What people do is you usually point your thumb in the direction of propagation, all right. In this case, you are having x axis to be horizontal, y axis to be vertical. So, you can take your right hand and keep your x axis like this, y axis like this, and then you can say that the propagation direction, this is your electric field components, your propagation direction is going to be your thumb, all right. If the thumb is like this, then it is slightly confusing, because then what they do is they take the left hand, all right, and then they point the thumb to the direction of propagation, and then they look at whether you can curl like this, all right. If you are curling like this, it's given some name. If you are curling like this, it's given some other name. What it means is whether you sweep the ellipse clockwise or anticlockwise. Okay. So, they will say that one of them is left-handed polarization, another one is right-handed polarization. A terminology that is also used is clockwise, counterclockwise, etc. But most of the times, unless you specify some reference, it is very confusing to figure out what is clockwise, what is anticlockwise, what is left, what is right, etc. But it is enough to know that these are two different kinds of polarization. One is going this way and the other one is sweeping this way. Okay. Both are possible. So, then what happens if I go back to my case, right, and I just make these unequal. Okay. This is first thing that we will see. I made it pi by 5 again. Okay. Still is an ellipse. In this case, it is going in the counterclockwise direction, all right. So, I can always point the left hand thumb to be going out, and it is doing this. So, one can say that in the way I am observing, it is a left hand elliptical polarization, right. Okay. So, the criterion for left hand elliptical polarization should become clear. You can have some value of E x naught, E y naught. The angle is not 0 or pi or 2 pi, it is some other angle. If it is a positive angle, you will have what is known as left hand polarization. If it is a negative angle, say negative pi by 5, you will have the ellipse being swept in the opposite direction, and that is known as right hand. So, these are some things that you may have to remember over a period of time, but if you do not remember, you can always figure out with respect to time what is happening, and then come to a conclusion as to whether this polarization is left hand elliptical, right hand elliptical, etc. Okay. Now, we will go to another case. Okay. Let us keep it as it is. E x naught is 1, E y naught is 2, and let us just look at the case where it is pi by 2. Okay. So, 0, pi, 2 pi is something we have seen. We have seen some other random angle pi by 5. Let us have a look at pi by 2 also, all right, and let us run this. Now, pi by 2 means that on the left hand side, x will reach 0, y will reach the maximum at the same time. Okay. So, the top left plot, you will notice that whenever y reaches maximum, x will reach 0. Okay. And whenever x reaches maximum, the y component will reach 0. That is what the phase difference of pi by 2 means. It did sweep an ellipse again, okay, and in this case the ellipse is going like this. So, I can curl my fingers like this, pointing to the direction of propagation. I can say that this is left hand elliptical propagation, all right, and I can say that the major axis is aligned like this, minor axis is aligned along this direction, etc. I can give more parameters if needed. Okay. Now, one thing I can do is I can see, suppose I make E x and E y to be identical. Okay. Clearly, on the top left plot, I can see that they are 90 degrees out of phase. So, whenever the maximum happens for the x component, minimum happens for the y component, all right, and vice versa. And we notice that the locus that is swept by the resultant is actually a circle. The circle is once again a special case of an ellipse. It just means that the major and the minor axis are identical. So, in this case E x naught was equal to E y naught. So, you ended up having an ellipse with equal major and minor axis. So, this is a circle. Once again, this circle is being swept in this direction, which means that you will have to see which way your fingers will curl, alright, your hands will curl like this, right. If you wanted your hands to curl the other way, you can always make it minus pi by 2. Okay. Now what happens is it's going in the other way. So, I cannot curl my left hand fingers this way. So, instead you point your right hand thumb to the direction of propagation and see where your finger bends. So, you call this as circular polarization or right hand circular polarization. Okay. So, I think this should be giving you a clear picture on what the polarization of electromagnetic wave is very clearly. Okay. Now, it is not necessary that the angle is exactly pi by 2 or minus pi by 2, it can be 2 pi plus pi by 2, it can be pi plus pi by 2, it can be 3 times pi by 2. So, let us see if I have 3 times pi by 2. Okay. So, it just needs to be an odd multiple of pi by 2, right, for it to sweep a circle, and Ex and Ey have to be identical. So, I think even if you do not remember the equation of the ellipse that we got before. So, finally, at the end of last lecture, we had written down an equation Ex by Ex naught square minus 2 Ex Ey cos phi by Ex naught Ey naught plus Ey by Ey naught square is equal to sin square phi. This is the equation of an ellipse, but the way it is presented, many people may be finding it difficult to figure out that this is an equation of an ellipse, all right, but this is what it is, all right, and the ellipse is the most general case. Ex not equal to Ey is a general condition, can be equal to Ey also, and when the phase difference is equal to 0, pi, 2 pi. So, let us go ahead, refine our observations with whatever we have seen and make this a little bit more concrete, okay, so that you are able to remember the things that is going on in the simulation. Okay. So, whatever we have seen, we will summarize first. Okay. Okay. So, for the linear polarization, it does not matter what your Ex naught, Ey naught was, okay. One could be 0, another one could be anything, one could be more than the other, etc. But the most important thing that we found out was the phase could be 0 or pi or 2 pi, 3 pi, etc. Could also be negative numbers, it could be minus pi, minus 2 pi, minus 3 pi, etc. Okay. So, it just means that you have a positive or a negative integer multiplied with pi. Okay. So, I will just write down that positive or negative integer. Okay. This is what is meant by linear polarization. Okay. Second case that we saw was elliptical polarization. Okay. It is a general case. Okay. So, we say that Ex naught is not equal to Ey naught, okay, making a general case, okay, but Ex naught could be equal to Ey naught also, all right. Which means that this condition is absurd, you can remove this condition totally, all right. So, it could be any value, whether it is equal or not, does not matter. Phi is say not equal to, right, 0 or pi or 2 pi, 3 pi, etc., that corresponds to linear polarization, all right. So, phi is not equal to okay, 0. Now, in this case phi not equal to 0, right, we write down that You could have both the components to be equal, you could have both the components to be unequal, you will end up sweeping some kind of an ellipse. Okay. Now, when we say phi not equal to 0, pi is also something like that, right. Pi by 2 is also something like that. So, we have to say that suppose it happens that phi is equal to pi by 2. The only way we call this an elliptical polarization is all right. If phi is equal to pi by 2, okay, we know that it can sweep a circle, and in general case circle is an ellipse with major and minor axis equal, but people find it confusing to call the ellipse a circle. So, we just say that Ex naught is equal to Ex naught is not equal to Ey naught and the face is pi by 2, then you will still end up getting a ellipse. Okay. And the last part is circular polarization. Here it is abundantly clear that phi is some odd multiple okay, it is m by 2 plus 1 okay, is some odd multiple, it is an integer, okay, it is an odd multiple. To be very clear, I will just make this odd multiple of pi by 2, could be plus or it could be minus, and the other condition is Ex naught is equal to Ey naught. Okay. In the case of linear polarization, we do not have anything known as left hand linear polarization or right hand linear polarization, because it is just going along one direction. In the case of ellipse and circle, you could have left hand or right hand, it depends on the frame of reference that you are using. So, it is very tough to explain directly, right, without making some diagram and saying that this is the direction of propagation and you have to curl your hands this way, right. And when somebody says counterclockwise, clockwise, it becomes confusing because you have to give a point of reference. Okay. What is clockwise from this side will look like counterclockwise on the other side and all that. So, the frame of reference in all these cases has to be very, very clear, then only it makes sense. Otherwise, absolute specification is much better. Okay. Say that Ex, Ey is so much, phase is so much, then I think people will be able to reproduce what is going on, rather than saying left hand, right hand and all these things. Now, there are some uses of this polarization compared to say transmission lines. There are some different uses over here, right. Polarization is a property that we manipulate on a day to day basis. Okay. If you buy some sunglasses, okay, you will have something known as polarizing sunglasses, okay, which means that definitely it has got a film that allows some polarization to pass through, some polarization to not pass through. Okay. In fact, the LCD screens that you will have in phones, LCD, not AMOLED screens, LCD screens, okay, and TFT LCD panels, all of them emit only at one polarization. If you did have a polarizing sunglass, all right, and if you hold it in front of you in between the screen and you rotate this glass, you will notice that there will be a point where the screen will appear only white, you will not be able to see what is written. Okay. It is a simple test to figure out whether the sunglass sold to you is a polarizing sunglass or not, all right. So, all it means is that we manipulate it on a day to day basis, and there are also some observations which are interesting. Okay. The reason for having this polarizing sunglasses seems that most of the times the glare that comes from shiny metallic objects is of some polarization. The rest of the useful information is of some other polarization. So, to avoid this shiny thing coming to your eyes and blocking your field of view, what they do is they allow you to have a polarization axis, which will allow you to pass electric field only of some specific polarization. Of course, these are materials made in some way, we are not going to be dealing about them, but it is possible to make materials which will allow polarization only in one direction, and those are known as polarizers. Okay. Also, it is quite possible that when we are talking about glasses, to have some polarization in the left side and some other polarization on the right side of the eye, okay, or the left and the right eyes could have glasses which have different polarization. For example, you could have only the glare coming to one eye and the information coming to another eye, all right. And the way the mind reproduces this image is all slightly complicated because we have stereoscopic vision, right, which means that we make some information about space with these eyes. We also try to estimate the depth with these eyes. Okay. So you can change the depth perception by playing with polarization and all that. So one of the common techniques that people use while making some movies long time back, not now, long time back, they used to shoot a scene of a movie with say multiple cameras. One camera will have a polarizer that will allow one direction of polarization, and the other camera placed in a different angle will capture the other polarization, and then they put together and then they project it with some coherent source. And what happens is when you wear these kinds of glasses with one polarization here, another polarization here, you start getting slightly different information through your glasses, and your mind will try to be creating a depth information that is different from watching a conventional movie. So people have played with it in the past to create 3D movies. But one of the things I said was it was done long time back. Now remember that when we talk about polarizing glasses, etc., we talk about horizontal or vertical polarization, etc. So it will have a specific axis along which the electric field will be allowed. So all the other axes it may not allow, the other axis it will not allow any electric field to be passed at all. That's the property of the material that's being made. And it was found that it's not particularly suited for movies when you use linear polarization, because you will have to stay with your head rigid at a fixed position. Once you start rotating your head this way or that way, you start getting very different kinds of information, right? So long time back, for the preliminary demonstrations that you can play with the depth perception, linear polarizations were used. Later on, people started using right and left circular polarized waves for cheating the depth perception of your eyes. So that even if you rotate your head one way or the other, you don't miss the depth perception that the producers wanted you to have. Okay. So nowadays they make use of circular polarization. One eye will get left hand circular polarized, and the other eye will get right hand circular polarized, and your mind will start putting these together in different ways. Of course, they are shot in different ways, so you will get a different depth perception. So polarization is a property that we do manipulate quite often, all right. It's I think a very interesting property because there are also findings that certain types of things have only certain kinds of polarization. It's also interesting that in the older ages, not sure about now, we used to have two ways of mass communication. One was radio and the other one was television, all right, and the TV was analog. Okay. And one of the things that we would notice is that when you held a radio in front of you, the antenna always goes up perpendicular to the ground. That's how you will catch a radio signal. Whereas if you looked at the rooftops of the houses in early days, before your cable TV thing, there used to be antennas, right? It used to have two rods and some kind of a loop going in between. They were mounted always parallel to the ground. All right. So the radios had antennas going up and the TV had antennas going parallel to the ground. Why did people not mount it this way or the other way, etc.? All right. Why did everybody mount it parallel to the ground on their rooftops? That should give you some idea that it has got to do something with polarization. Okay. So the TV signals were using some polarization. The radio signals were using some orthogonal polarization. All right. And that's why they were being used in different ways. Okay. Which means that you had to adjust your antenna to a specific angle or orientation with respect to the ground in order to receive maximum signal for that particular information. Okay. This can also lead to very interesting thoughts on how to perform some emergency communication in a practical setting. We'll take up a problem in the next class and we will see how this can be used. Okay. So we'll see how a combination can be used. But at this stage, I think you should understand that polarization is a property. It can be manipulated, right? And there are practical uses of these for several years, right? And if you did have some polarizing sunglasses, and if you did have non-AMOLED, that is TFT LCD based screens. You can always put it in front, rotate your glasses, and you will find that everything is distorted, only the backlight will come. Okay. You could try these small things, right.